Welcome to Mastering Solutions. I've drawn a converging lens for us here with the arrow. And then we have our focal point 1 and our focal point 2, and they tell us that the focal length for that is 9 centimeters. That's not super important right at this second. We'll use it to figure out the location later on. But to do the ray tracing first, they tell us that we're placing this splinter on our finger at 6 centimeters from the lens, so about right here. And we'll use an arrow to represent the object. Now we need to figure out, I'm going to do it a little bit smaller just so it's easier. I don't need as much space on the ray tracing. That's okay. And so now we're going to use ray tracing to figure out the distance, and then we'll do some calculations to find the numbers and the magnification. Remember, anytime you do a ray tracing, remember three things. We're going to have parallel to the focal point, parallel to the focal point, center of the lens, and then focal point to parallel. If you remember this, you can get through any ray tracing diagram that you have to draw on a test. And so to do parallel, we're going to start at the top of our object here. And when we have collimated or parallel light rays, it will focus by definition through the focal point. So right like that. Now we're going to start here, and then we're going to do one through the center of the lens. You can see already in our picture that these are not ever going to intersect. They're actually diverging away from each other, and that's because we're on the inside of the focal point. That'll be really apparent, of course, here when we do our last one. So we're going to go from the focal point as if we were going straight to the top of the object, and then now, since it's coming from the focal point, we'll have perfectly collimated or parallel light rays. And so now these are never going to intersect, so we have to extrapolate them backwards because we're going to get a virtual and upright image. So if we start here and go back, there's that one. Then we'll extrapolate our second one coming from the center of the lens. That looks pretty good. Whoops. Yeah, that's okay. I think I messed it up a little bit when I moved. And then like that. I know that's not perfect. I think I messed up on my focal point distances. If they're not exactly the same distance, it'll mess up your ray tracing. As we've talked about on some of the previous problems, if we were to do this on graph paper and be very, very precise in our locations and our sizes and everything, you can be very accurate and get the exact same answer as if we were to calculate it mathematically. But this is good enough for here. So we have our image, and it is on the upstream side of the lens. So we have a virtual image, and that's of course going to be upright. And now let's figure out how far away from the lens it is. And we're going to use the thin lens equation to do that. We know that the thin lens equation, as we've done a lot of times now, is 1 over f is equal to 1 over s plus 1 over s prime, or the object distance plus the image distance equals the focal length. And then we're trying to solve for the image distance. So we'll subtract 1 over s over. So 1 over s prime, or the image distance, is equal to the inverse of the focal length minus the inverse of the object distance. So we have 1 over s prime is equal to 1 over the focal length, which we said has a 9 centimeter focal length. So we have 9 times 10 to the negative 2 meters minus the the object distance, which we said was 6 centimeters. So we have 6 times 10 to the negative 2 meters. We have a converging lens, so this will be a positive value. And so we have 1 over 9 times 10 to the negative 2 minus 1 divided by 6 times 10 to the negative 2. So that's going to give us negative 5.5, negative 5.5, and the units for this will be in diopters. If we take the inverse of a diopter, that'll give us meters. So we take 1 divided by our answer, and we have negative 0.18 or negative 18 centimeters. So our distance from the lens is negative 18 centimeters. The negative indicates that it's on the upstream side of the lens, which agrees with our ray tracing that we did here. If we want to calculate the magnification now, we can use the magnification equation, which is equal to, the one that we'll use at least, is the negative image distance divided by the object distance. So now that we have the image distance, we have negative 18 centimeters. Since we have centimeters for both, as long as we have the same units, it's fine, and we don't have to put it in meters, but if you did, it's fine as well. And then the object distance we said is 6 centimeters. Be sure to include the negative here and to not forget that we're going to have two negatives. There's one for the equation and one for the answer. So we have 18 divided by 6. That's going to, 6 can go into 18 3 times. So we have a 3 times magnification of our image, and it's 18 centimeters from the lens. And you can see we kind of got close on our ray tracing. This is 9, and if we were a little more precise, this probably would have been back a little bit further. And this is probably pretty close to about 3 times bigger than this. But in either case, these are your answers: 3 times magnification and 18 centimeters upstream of the lens.